Hey everybody, Tom Cherry Holmes here with the FujiNet project, and I wanted to do a pair of videos showing how to write a new game in BASIC for the FujiNet. In this case, a simple light cycles game. Light cycles, for those who don't know, is a very simple game in which you are two players who are racers inside of a field. You race against each other. You start off literally facing each other, going toward each other. You can move with the joystick. And as you move and change direction, a barrier forms behind you, a barrier that can be potentially hit by the other player. If the other player hits your barrier, you get a point. If you hit the other player's barrier, they get a point. If you both hit each other at the same time, this is what is essentially called, and you're going in the same direction, this is essentially a draw, and neither player gets a point. It's a simple enough game to write, and so we're going to spend this first video writing the core mechanics of the game that we will later pick up in part 2 and add network routines to. To start, we're going to use an existing disk as a template. We'll go to atariapps.errata.online, go to the Games folder, pick up a copy of Reversi, which has everything that we need to write a new game in BASIC, as well as provide a nice example that you can potentially pattern off of. We'll go ahead and put that into drive 1, mount it as read-only. Then we will exit back out. I'm going to go to my local file server here and store my work disk that we're going to work on our game here. You can, of course, also put it on the SD card slot as well. We make a new disk. We call it something useful. It's a 90K disk. We don't need much more than that. Are we sure? Yes, absolutely. And we're going to place it in drive 2. It's now ready to go, and we can literally tap the Option key to go. Since this is the Reversi game, it will boot up into Reversi automatically here. This is fine. All we have to do is tap the break key. We tap the break key, go to DOS, and we'll do some basic file management here. If we look on drive 2, of course, we see that this is a blank disk that hasn't been formatted. We need to go ahead and format it and copy our files over to it. Luckily, there is a utility on the first disk, dupedisk.com, which will do both tasks for us. We go from the first disk to the second disk. We format the second disk. Go ahead and duplicate the disk for us. That's all we need to do. Copy the same disk again, no, and if we look on drive 2, we will see our disk ready to go. We're essentially done here, so I take and press the reset key on the FujiNet and do a cold start. We'll go ahead and remove the Reversi disk and our work disk, and put our work disk back in as drive 1. Making sure to mount it as read-write. If you want to make sure, ensure that the first slot is indeed mounted as read-write, because we're going to be working on this disk. Tap the Option key, let go, so that BASIC loads. We're ultimately going to see that this disk works exactly the same as the Reversi disk. Let's do a little maintenance here. We don't want the Reversi game anymore, so we'll go ahead and remove it. Then we need to actually modify our startup so that it automatically loads our game, but we may not want to do that just yet. So for right now, we'll simply remove the startup exe. That leaves us with our auto-run-sys handler, which contains our in device, a copy of dupdisk for later, sure, and a copy of do, which we will use to automatically load our game when it's ready. Now that we go back to the cartridge, we see that we find ourselves in a basic environment, and we can now begin to write our game. To start, we need to take and set up our playfield. We'll go ahead and start at line 100 here and do a little go sub to 1000, which will initialize our playfield. This is a simple subroutine that puts us into graphics mode. In this case, I'm choosing graphics 3, uses color number 3 for what we're about to draw, and plots a square around the playfield. That is everything that we need in order to actually take and draw our playfield. We'll go ahead and put an end here at 999 so that the program stops at this location. Oops, new. We'll do that again. Always make sure that your program is nice and clean. So sorry. We'll do that again. So the first thing we need to do, go sub 1000. And 1000, of course, sets up the graphics mode, which also clears the screen and gets it ready for graphics mode. We set color to 3, which in this case right now is the blue color. We plot our initial pixel at the top left corner of the screen, and we draw a line to the right side of the screen. Since this is graphics mode number 3, there are 40 pixels across, numbered 0 to 39. And since this is graphics 3 with a text window, this is 39 pixels across with 20 pixels down, numbered 0 to 19. So this gets us to the right side of the screen. Then we need to go to the next one, which is 0 to 19. Sorry, let me just make sure I do this right. So 0, 0, sorry, 39, 0. 39, 19, 0 to 19, and 0 to 0. This draws a perfect square around the screen, and once we're done, that's all we need to do. We can simply return. We also need to add an additional line here to end the program so that we don't accidentally spill over into our subroutine. Running this, we see our nice little drawn square here, and if you see right here, you'll see that the cursor stops right there, and the graphics right up above draws a nice perfect square, just showing that that actually works. And just to show that it's actually there, we'll take and change the color real quick to color number 2. Boom. So we'll put that back because I want to use color 3 for that. And the next thing that we want to do is we want to have a routine that sets up our initial values that we're going to use for the game. And we'll call that line 1100. This will be run every time that the game restarts itself to set initial values. Now we need some variables to keep track of certain things. We need X and Y values for the left player and for the right player. And we need to set those initial values. To look at each one of these, it's really very simple. We want to place the left player on the left side of the screen at X position 4. We want to place the right player on the right side of the screen at position 35. Now these are 4 pixels away from the screen, from the side of the screen, taking into account the drawn border. We want to take and put them actually at the same position for LY and RY. So putting them roughly in the middle of the screen, accounting for the text window. Then we want to make sure that the left direction and right direction for each of these is facing the appropriate way. That is, the player on the left is going right, the player on the right is going left. And these values are literally directly derived from stick positions. Currently, I have my joypad right here. It's not going anywhere, so when you read stick 0, it will be 15. If I change that value now, if I push to the right, you'll see that that value is 7. If I push to the left, you'll see that that value is 11. That's where those values come from. This is everything we need to basically set up our initial game state. Make sure that those things are there. We go ahead and make another line here to end, because I don't know what else we may want to put in here, but this is kind of a little area that I've reserved for setting up initial variables that we want to be able to set for each round of the game. For right now, it's just one line. So, sorry, return. So there we go. Boom. We have two routines here. And we'll go ahead, now that we have that, we go ahead and call go sub 1100. We'll see the result right here. We draw our playfield, we set our initial variables, and you're not going to see much of any difference here yet. But wait, it's coming. Don't worry. We'll go back, and now we'll start actually implementing more of what we actually will need for this to work. We continue on with the main loop here. This is essentially, this whole section is going to be called as in one big loop. So we start off by picking the first color and plotting the point for that color at that particular point in time. We do the same for our right values. And keep in mind, remember that we set these in 1100 to some initial values. So now that when we run the program, we're going to see two dots appear in our initial player start positions. Moving onward, we need to now start checking for some collision detection. And for that, we will set a variable x to lx, y to ly, and we will call a routine at line 1, which we're going to write in just a moment, and get the resulting color back. We're going to do the same thing for the right player. So we're calling this routine that we are about to write at this particular moment in time. Let's go ahead and set some space. And we're going to go ahead, since this program is going to start at line, we know we want to start at line 100, we're going to go ahead and just bounce over this piece that we're going to write here. And since this routine is going to be called repeatedly, we want this routine to run as fast as possible. And therefore, when we take and go sub this routine, we want this to show up as quickly as possible, because when you do a go to or a go sub, BASIC will search every line of the program starting from the beginning to the end to find your line number. So programs with smaller line numbers, so routines with smaller line numbers get executed faster than routines with larger line numbers. So this routine is actually very simple. We say if D is equal to, turns out I need to make one adjustment for both of these. D equals LD. D equals RD. My bad. So this is immediately a check. If D is equal to 14, this is going up. then X doesn't change, but Y does. We can actually do an optimization here. If D is equal to 13, then and we actually do need to do Cx is equal to X. My bad. This is what I get for improvising. So, what we're doing here is setting a variable here for a pixel that we're going to check. If we're going up, then we want to check the pixel position. If we're going up, we want to check the next pixel position up. So we subtract 1. However, if we're going down, then we want to check the next position down. So we add 1. If D is 11, then Cx is now, and Cy doesn't change. Conversely, if we're going right, then we're checking the position to the right. Finally, we use the locate command with the values that we have generated above with our color at that pixel position in CC. Locate takes 2 values and as input, the X and Y position of the pixel you wish to check, and it returns the color at that pixel in the variable that you ask for. This is our collision detection routine, right here. So if we go ahead and run this, we won't see much of anything change. We'll go ahead and save this right now for good measure. We won't see anything change. And in fact, if we look at the color that we pulled back, you'll see that nothing has changed because the color to the right of the orange pixel is black. The color to the left of the green or yellow pixel is also black. So that's color 0. Okay. But believe it or not, that's the core of our collision detection right there. Moving on, let's go ahead and insert in some logic here. Now that we've got these values, we can do something with them. We need to check for, essentially, for each time that we run this loop, starting at 120 and ending down here, we need to check for 3 eventualities. One is that both players are going toward each other and hit each other, in which case it's a draw. We need to check if the left player hits the right player's wall, and we need to check and see if the right player hits the left player's wall. This is easy enough to do because we already have the color values of the adjacent pixel brought forward with us and put into their respective variables here. So all we have to do is 3 if statements. The first one checks for the draw condition explicitly. And if so, we'll go to line 1200. The second one checks for the left player colliding with the right player's wall, in which case the right player wins. Otherwise, we check for the right player colliding with the left player's wall. And again, we're not going to see much of a difference here, but we'll go ahead and run this anyway. Boom. Again, not much changing. But we have some basic calculations happening. We'll go ahead, and now we actually need to write two more routines to help us out. The first updates the pixel position for the next frame, for the next run through the loop. And that starts at line 7. If the left is going up, then we need to go ahead and set the new direction here. If the left player is going down, then we need to set the next pixel down. If we're going left, seven, eight, 9, 10. And conversely, we'll go ahead and borrow this for the next few lines here and change each of these for the right player. So we need to do this check for not just the left player, but for the right player as well. So now if we look, we have a routine that updates the player's position. And we go ahead and return. Hold on. We also need to write one more routine, which we'll go to in just a minute. But for right now, this is enough to show that this will start to work. We need to finish up this routine. And go sub 7. And again, not much is happening here because we've only run through this with one iteration. To make this completely work, we need to go ahead and go back here to 120. Boom. Okay. This error 12 is absolutely fine because if we list that, we see our draw condition has been reached, and it's trying to go to line 1200, which doesn't exist. Well, let's go ahead and fill that in. $1,200 is the draw condition. And we'll go ahead and make a little routine here. And all 2000 is essentially a simple for delay loop. That's it. Boom. So this is where we stand right now at this particular point in time. We loop through each one of these, and if we reach a winning condition, then we call 1200, 1300, or 1400 appropriately, and then immediately jump back to line 100, which reinitializes the game. It calls the playfield, reinitializes, redraws the graphics, and everything is good. Let's see how this turns out. Boom. And as you can see here, this is working exactly as expected. Let's do some unit testing. Recall that we initialized these values in line 1100. So if we change these values to something else, let's say we want the left player to start off going up, then we should see him go up. Of course, the right wins, just as it should be. Oh. And again, we can change this value again. Let me get my notes, because I can never quite remember all of these. So let's say we want to go down. And we want the right player to go 13, 14 down, 14, 13 down. Boom. 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 Okay. So directions seem to be working, and if I take and change here, let's check for an eventuality here. Let's say we want 14 and 13. So one player's going down, the other's going up. Now, because this is an interesting case here, because there are fewer pixels going up than there are going down, the orange player gets to the border first, and therefore the other player wins. But you can see that this is actually working exactly as expected. So you can see that this is actually okay, and we'll go ahead right now and just set that back to where we were. So the left player should be going right, and the right player should be going left. And we're back to our draw condition. Boom. All good. To finish up this video here, I am actually going to take and put in a stub so that we can do some simple joystick control, so you can see how this will actually work. And with this, you'll have the basic bit for the core mechanics for a light cycle game. For this, we'll need one more subroutine. Sorry, 0 to 100. Yeah. Boom. And we'll put it here at line 16. And we'll simply say, if the stick is actually being moved in a direction, and we set the left direction to stick 0, and we'll set the right direction to stick 1. And finally, we'll return. We need to change the end of our loop to actually call this routine to check our joysticks. And with that, we should be good to go. I'm going to turn my joystick back on. I have 2 joysticks plugged in here. Bam, 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 boom. You can see that joysticks work for the left player, and the motion works for the right player. And so on. So now we have essentially the basic metrics, all the basic mechanics for our light cycle game done. And we did it in just under 30 minutes. In the next video, I'm actually going to be talking about how to take our game that we've built here and moving it over onto the network. Adding routines to read and write from the FujiNet to handle player connection and registration, and so on. So until next time, guys, have fun.